In this video, we will be using Newton's second law to solve the following problem. A snowboarder begins at rest at the top of a slope 67.2 meters long at an angle of 23 degrees to the horizontal. We can consider the coefficient of friction between the board and the snow to be 0, and we will neglect air resistance. Then we are asked, first off, what is her velocity at the bottom of the slope, and then how long does it take her to get down the slope? The first step in our problem-solving process is always to draw a diagram showing the information that we're given and showing the forces acting on the object. So here is a diagram showing the information that we were given at the start, with the snowboarder going down this incline of 67.2 meters long at an angle of 23 degrees to the horizontal. And note at the top of the slope, she starts from rest, so her initial velocity is 0, and we are asked to find the final velocity. So now on this diagram, we are going to draw the forces which are acting on the snowboarder. And in this first situation, it is very easy because there are two forces. The weight force, which, remember, is equal to the mass times the acceleration due to gravity, and the normal force, which, remember, is always perpendicular to the slope. There is no friction force, there is no applied force. These are the only two forces that are acting on the snowboarder. So we've drawn a diagram with all the information we're given, and we've drawn the two forces that are acting on the snowboarder. Second step is to choose a coordinate system. Now in this case, we could do the traditional X and Y coordinate system, but that would present us with some problems. Because if we adopt a traditional X and Y coordinate system, we would have to break the normal force up into components, and additionally, we would have to break the acceleration up into components. Her acceleration as she goes down the slope would have, in a traditional Cartesian coordinate system, would have both X and Y components. To avoid that extra work, we can redefine our coordinate system, because the only real requirement in the Cartesian coordinate system is that X and Y make a 90-degree angle. That's the only requirement. So X does not have to be horizontal. The positive X direction could be down the slope. And the Y direction does not have to be vertical, but it does have to be perpendicular to X. So we can draw in a new coordinate system. We just take the traditional Cartesian coordinate system and twist it so that now X is down the slope and Y is perpendicular to the slope. This is a very convenient coordinate system to use for inclined surfaces. And we'll see the advantages as we work through the problem. The next step in our problem-solving process is to ask ourselves, do any forces need to be broken up into components? If so, draw those components and write out formulas for those components. Well, with this definition of X and Y, we don't need to break up the normal force because it is purely in the Y direction. But we do need to break up the weight force, because with this Cartesian coordinate system, we have two components of the weight force. Let's call them WY and WX. WY and WX. Now, of course, WY and WX are perpendicular to each other. And this angle right here, the angle between WY and the weight force, is equal to the angle of the incline. In this case, 23 degrees. So that angle right there is equal to the angle of the incline, 23 degrees. So now that we know some of the angles in this triangle, notice it's a right triangle because X and Y make a 90-degree angle, and when we have a right triangle, we can use the trigonometric functions to find these two sides of the triangle. Let's begin with the sine function. The angle is 23 degrees. And remember, the sine function is opposite over hypotenuse. Now in this case, opposite the 23-degree angle is WX. WX. This is a departure from some problems we've done before, but you always have to be very meticulous about this. Don't try to memorize anything. Work through it. And the hypotenuse is this right here, mg. Rearranging the formula to solve for Wx, we now have a formula for Wx, mg sine 32. Turning now to the cosine function, remember the cosine function is adjacent over hypotenuse. And in this case, the component adjacent to the 23-degree angle is WY. Again, a departure from some examples that we've done. You have to be very careful and work it out every time. So now we have a formula for WY, which is mg cosine of 23 degrees. All right, so we have drawn a diagram showing all the forces acting on the object, 2 of them. We have selected a coordinate system that is useful for an inclined surface. We have decided that the weight force needs to be broken up into components with this coordinate system. We drew those components and we wrote out the formulas. And now we are ready to use Newton's second law to find out what we need to find out. Right, and so we have here the 2 parts of Newton's second law. Remember, since force is a vector quantity, Newton's second law is really 2 equations. One for the x components and one for the y components. Now this AX right here in the x forces equation is the acceleration that we are looking for. We want to find the acceleration down the slope so that we can find the final velocity. All right, and we can find that acceleration by looking at the x forces. So this is the acceleration in the x direction, the acceleration down the slope. The acceleration in the y direction as we have defined it here, well, that's going to be 0. Because the snowboarder does not rise up off the slope or sink down into it, her acceleration in our new y direction is going to be 0. So we're only concerned with her acceleration in the x direction because that's what will tell us the final velocity. So let's look at the x forces, or should I say x force, because there is only one. There is only one force in the x direction, and as usual, when there's only one force, adding them up is rather easy. Now Wx is down the slope, which we have called the positive x direction. And so we can say here that the sum of the forces in the x direction is simply Wx, and that's going to be equal to the mass times the acceleration in the x direction. Well, now looking at our components here, we have a formula for the x component of the weight force. So we're going to plug that in here. Now, you may notice that a problem with this problem is now solved. Some of you may have looked at the question and said, well, we don't know her mass. How can we solve the problem? Well, you see, the mass drops out. It is true that if she has more mass, she feels a stronger pull. If she has more mass, she feels a stronger pull. But also, if she has more mass, she has more inertia. If she has twice the mass, she feels twice the pull. That's true. But she's also twice as hard for gravity to move. So those two things balance out, and in the equation, mass cancels out. This is why I always encourage you to do algebra before you do arithmetic. You never know when something might drop out. And so we are left with the acceleration in the x direction being g sine 32 degrees, and using a value of g of 9.80 meters per second squared, we come up with an acceleration in the x direction of 3.83 meters per second squared. Now, the reason we wanted to find this acceleration is so that we could find the final velocity. Now, we are not given information about time. We are not told how long it takes her to go down the slope. That is, in fact, something that we are asked to find later. So we turn to the kinematics equation that does not involve time. Kinematics equation number 3, which involves the final velocity squared, the initial velocity squared, plus 2 times the acceleration times the displacement. Now, looking up here, we see that the initial velocity is 0, and the displacement is 67.2 meters. And we just found the acceleration, so that clears the path for us to find this final velocity. The acceleration is 3.83. The displacement is 67.2. All right, and we multiply all this out, take the square root, and that gives us a final velocity of 22.7 meters per second. To 3 significant figures, which is the number of significant figures in this problem. So that tells us she has a velocity of 22.7 meters per second at the bottom of the slope. And then we have the follow-up question: how long does it take her to get down the slope? We have some options here, but probably the simplest is to just use the first kinematics equation. There we go. The first kinematics equation with a final velocity of 22.7, an initial velocity of 0, an acceleration of 3.83, and the time unknown. And when we solve this equation for t, we get a time of 5.92 seconds. again to three significant figures. Now I encourage you to go through these equations on your own. Make sure you can reproduce these results. And it's also an interesting exercise to try the other kinematics equation, this one right here, to see if you can get the same result for the time. All right, see if you can get the same result for the time to go down the slope, 5.92 seconds, using this kinematics equation right here. So all in all, it takes her 5.92 seconds to get down the slope, and when she reaches the bottom, she has a velocity of 22.7 meters per second.